Alright, this is part 1 for Ozbat Project 4. Make that 2D real quick. Which means we're just going to be doing a couple different conditions for a sphere, or I guess really just a circle in 2D flow. Alright, so let's start up. First off, let's do it in the Z-plane. Let's get our circle centered up. That's going to be of diameter 1 meter, as specified by the professor. And then we're going to get our test area, and that is going to be 10 by 10. These. There we go. 10. And we will get equal length for these two sides. And then we will get symmetric about the center here. And we're going to do horizontal between this and this. Please. Dimensions. Horizontal between this and this. We'll do it as 3, just because we want to have more of the test section behind the test article. That way we can see more of that wake developing. Actually, let's do 2, honestly. Alright, that looks good. Go ahead and grow a surface down from that. Select all that sheet. Take these guys back off. Apply. Generate. And now we're going to do another one of these. And from here we're going to take a rectangle. Throw it on just like that. Dimension it. It's going to be 2. Constraints equal length, so we want a square. Now let's get it symmetric. Perfect. Now draw get some lines off of that so we can partition up our test area. Just like that. Now we're going to select this guy. Face split it. Target face will just be this right now. Like this. Target geometry. Means sketch 2. Can you just apply it like that? No. Sketch 2. We need where's our... Am I tripping? There it is. Not you. Oh, we're missing 2 lines actually. I'm jumping the gun here. Let's sketch those in. Get rid of you, please. I need these. Alright, now we'll get that face split in. Face, this guy. Geometry. These should be 14, 14, perfect. Generate. Looks good. Can we name our inlet here? Or do I have to wait until the other thing? I can't remember. Let's see. We can. I don't know if this is where I want to do it though. I'm gonna wait for the mesh actually. Get out of here. This looks good. Go ahead and update and edit the mesh. Still recording, beautiful. Gonna time skip to when this mesh is open. Alright, here's our mesh. Looks good. Never mind, we don't want it to look like that. We want face meshing. Spurs with lateral. Yeah, that was good. Generate like that, please. Perfect. And now from here, we're gonna go ahead and do some sizing. Not off the faces though. Doing this off of these guys. See, I wrote down what I wanted to do for these. Do those as 30. How many others are 30? 2. We'll do these as well while we're here. These will be, I'm sorry, we need to apply that. Element size now. Number of divisions, 30. Default, no curvature please. Hard behavior. Looks good. Throw another one on. We want another sizing. The middle this time. That's gonna be another division. 50 for this one. Yeah. No curvature. Hard features. Looks good. I've done these. These are 30, and we're gonna have a bias on these guys. No curvature again. Hard features. Bias, please. We'll do like this. Fact will be 4. And then these 3 are typically backwards. Spin those guys around. Looks good. Now let's see, we have those. I think it's just this guy over here now. These are going to be division, 100, no, hard. See if this gives us what we want. Looks good. All right. And then from here, we just need to label our inlet. Outlet. This will be labeled symmetry. So that will symmetry. Maybe symmetric, I think. I think maybe either, I don't know. But that's just a keyword so that it automatically treats itself as symmetric. This will be our wall. Inlet, outlet, symmetric, wall. Looks good. Now let's do the setup. Or actually, we need to update the mesh. Or, never mind, did it for us. Wonderful. We'll time skip to when the solution is open. Alright. Now we're in our solver. Everything is looking good. Our inlet and outlet were properly defined. We're going to go ahead and start with our inviscid case. So we'll set this inviscid. Okay. All this is the same. Materials is the same. We need to go to boundary. For this, we're going to have a velocity of 5 meters per second. And we will actually also keep that for our viscid laminar case. We're going to apply that. Now we also just want to check that that's symmetric, that's a wall, interior, outlet, interior, inlet. Sweet. So those are all referenced properly. Good. And then I think it was, where are we, is our, I'm tripping, where was it? It's monitors, residual. I'm just gonna add a 0 to these. Board monitor. And we should be good to start initializing. Go ahead and initialize. Did it do it? Yes. And now, calculate, we'll do this with 1,000. That's good. Run the calculation. And I will unpause when we got it. Alright, the calculation has completed. Let's take a look. It said, we want velocity contours with streamlines. We'll do that first. So we'll go to graphics, get a mesh running. Or sorry, not a mesh, contour. Velocity magnitude. We'll do this inviscid V. We'll copy that inviscid just for our nomenclature moving forward. That's good. About what we expect and what I've seen in my past runs. And then since we're already in contours, we'll do the rest of them too. Inviscid top P for our total pressure. Inviscid dyne P for our dynamic pressure. And then inviscid, which one's left? Stat P for static pressure. And you can pause the video for each of those as they showed up, but those are our pressure contours for the inviscid case and half of what we need for our velocity. We also need to do a vector for our velocity. We're going to skip a couple just because this thing gets crowded pretty quickly. Yeah, that looks fine. Let's actually rename that. Inviscid vec V. Close. Let's get this to merge this together with the scene. Give this some transparency. Inviscid V vec. Like the Elder Scrolls. But there it is. Looks good. And I'm not going to save any of these because I already did some farming off camera and got our inviscid, viscid, and viscous turbulent cases. And then let's see. We also need, I believe we want our velocity and CP. CP distribution over the surface, velocity distribution over the surface. Okay. So we'll go and do CP since it's right here. CP. Put over the surface, we'll just pick the wall, save and plot. That's what we would expect it to look like. It's what we've seen in the past run times. And then open up a new one. DXY. velocity, velocity magnitude, wall, plot. And again, that's what we had as before. I guess those are just text files, so I can't really reference them until I replot those. But that's about what we would expect. So that's all the deliverables for this run. Velocity contours with streamlines, pressure contours, velocity distribution, CP. And then we also need drag coefficient, which we can go to reports, forces, and have them print that out. And that gives us our inviscid drag force. So I'll just write that down, 1.6219044, which we can then convert into a drag coefficient, which I'll do off camera, just so I'm gonna have to do all those. And then these will actually auto update as I rerun the model. So now that we have all that, we'll go ahead and switch to a laminar model. And it does say to pick a proper velocity for laminar and turbulent based on the Reynolds number. And based on the Reynolds number, if we rearrange that equation, we see that that cutoff is at 7.3 meters per second. So we can just leave it at 5 for this. So we'll change it to laminar. And we can go ahead and initialize and rerun. We'll come back to you when that's loaded. Alright, it has just completed, and I kind of wish I unpaused earlier because it actually just cycled through every single graph that I had. But once this responds, I will open these up just to show them really quick, and then we'll do the turbulent case. And that'll be it for the video. I'm actually going to pause again and wait for this to respond. Alright, are we good? We're good. Okay, we're here. Start looking at these. Static pressure. Dynamic pressure, we see that elongated wake. Total pressure. Actually, leave this one. And of course, because we are now inviscid, we're getting 0 on the surface, which makes sense. And our CP has a flat cutoff. And then, where is our C? There's our velocity. Alright, and then we just have to show our forces, which are significantly increased for 6.077. It's actually a little bit different from the last runtime, but I guess that makes sense since this is very reliant on the numerical part of the program. 6.0772792. We actually can compare these since where is my file manager? You see a similar plume, but we have a much more obvious reversal region here as compared to our original calculation, which I think I'll actually probably use these ones because these are much cleaner. But we do see the general trend regardless. So I'm going to pause, save all those, and we'll do turbulent. Alright, those have all been saved. Now we'll do our turbulent. We'll just do KAPs, 2 equations. We'll leave all this the same. So Okay. And then we do need to change our velocity because right now it's actually below the turbulent regime. So the cutoff is 7.8 or around that, I think 7.8, 7.3. But we're just going to change it to 15 so we're very well within that region. And we'll leave the intensity and viscosity the same. And now we will rerun and take a look at those. Alright, now we got the turbulent up. I'm just gonna save it while I pull them up and you can look at them as we go. Pull that up. So static pressure. Perfect. Dynamic pressure. Total pressure. Velocity with streamlines. Again, we don't have any velocity on the surface because it is viscous. We actually see very similar CP recovery. Again, can't really show it in text, but I believe this actually recovers a bit more. I guess the axes could always change, so without actually looking at it now. At least from a simulation standpoint. Did we save that CP? We didn't? Okay. Alright, so we've gotten the velocity contours with streamlines for all cases, pressure contours for all cases, velocity distribution on the surface of the cylinder for all cases, CP distribution on the surface of the cylinder for all cases, drag coefficient. We've gotten the we've got force for this one as well. Which we should expect this to be higher. There it is, 48.806. $806,587. All right. For the wake patterns and drag with experimental data, I think we're just doing the simulation in the video technically. So we simulate all this stuff already. So that is the video. The actual data, what we've collected, will be in the report. Thank you.